So in our last lecture, we had left off with looking at our unit of study known as chemical reactions, or chemical equations of reaction, and how we know chemical reactions are going on, how we express them. We started off with the 5 evidences of a chemical reaction taking place, sort of a macroscopic, observable view, and there was 5 of these. A couple of them are right there: color change, the emission or absorption of heat, and that sort of thing. We had moved into the fact that sometimes we see abbreviations of the 4 physical states of our reactants or products. Not all the time, but sometimes we see that. And just essentially, in case you were curious about why these abbreviations are there, sometimes that is important. And lastly, we looked at the 4 general reaction types: synthesis, decomposition, single displacement, and double displacement types of reactions and examples of each of them. So what we're moving into now in this chapter is really the majority of the unit of study. It's called balancing chemical equations. And essentially, to balance a chemical equation means we have to allow it to adhere to the law of conservation of mass. To do this, numerals or numbers have to be put in front of some of the reactants or some of the products sometimes, in order to make sure there's the same number and type of atoms on one side of the equation as there are on the other side of the chemical equation of reaction. So here's, just as an example, here's a representative chemical equation of reaction, and CH4 plus O2 goes to CO2 plus H2O. Now, if we look carefully at this, we can see that there's 1 carbon on each side. However, there are problems with it because there's differences in the number of hydrogen atoms and the number of oxygen atoms on each side. On the left-hand reactant side of this, we have 4 hydrogen atoms and 2 oxygen atoms. But on the product side, we have 3 oxygen atoms and 2 hydrogen atoms as written. So this is a problem. We cannot have a chemical equation of reaction which does not adhere to the law of conservation of mass. Now, to fix this, if you look at the chemical equation of reaction down below, we are able to balance it, basically, again, allowing it to adhere to the law of conservation of mass by placing a 2 in front of the O2 reactant and the H2O product. In so doing, what we get, if we count all of the atoms up on each side, we find that they are equivalent on both sides. There's 4 oxygen atoms, 4 hydrogen atoms, and 1 carbon atom. Now, as far as numbering goes, it should be noted that if there's no numeral in front of a reaction component, such as here CH4 or the CO2 component, it is assumed to be the number 1. We just don't write it in there. We just write anything other than 1 in front of the the 2 or 3 or that sort of thing, in front of the necessary reactants or products in order to balance the equation. So the best way to do this is just to do them. We'll work through a number of different examples, and we should be able to formulate a methodology for which to attack other problems that we can do on our own, perhaps in the problem sets that are on Blackboard that you can try on your own. So as I said before, the goal is to place numbers or numerals in front of the reactants or products, and that number could be 1, where we wouldn't put a numeral there, but it would be implied to be 1, such that it always adheres to the law of conservation of mass. There's an equal number and type of atoms on each side of the equation. So here's an example problem down here. So how do we start one of these? How do we start? There are many roads to Rome, meaning there are a number of ways of working through this that you can carry out so that you will come up with a correct answer. A number of them could be lengthy. So what I'm going to be showing you is my way of doing this so that we can spend the shortest amount of time on these reactions. Typically, it's best to place a 1 or an implied one, in front of the most complex or largest component in the equation. In this case, that would be CH3OH. It's not always obvious. Sometimes there may be one or the other. It's okay. You could put a 1 in front of either of them. However, just may take a little bit longer. You may be erasing and coming back and putting other numbers in there. But let's put a 1 by CH3OH. By doing that, we have made a statement. And that statement is that if there's a 1 here, that means there's 1 carbon on this side, 1 oxygen, and 4 hydrogen atoms. So there better be 1, 1, and 4 on the other side. So how can we do this? Well, let's take a look in this case at if I put a 1 here, that means there's 1 carbon and 1 oxygen on the product side. There better be 1 carbon and 1 oxygen on the reactant side. Well, look over here, 1 carbon and 1 oxygen. So I'm going to place a 1 in front of carbon monoxide, or CO, and that takes care of carbon and oxygen on both sides. They are balanced. Lastly, what we see, if I have a 1 here on the product side, that means I have 1, 2, 3, 4 hydrogens I have to account for over on the reactant side. Well, let's take a look. This is the hydrogen containing component right here, and they come 2 to a packet. Frequently, we see diatomics, diatomic elements in these balancing chemical equations. 2 to a packet ultimately means if I need 4 of them, I'm going to put the number 2 right there. 2 times 2 is 4, and this in this chemical equation of reaction would be balanced as shown. So let's look at one that is perhaps a little bit more complex. In this case, they're all like this. We have our reactants, we have our products, and ultimately we have our lines in front of each of them. Inside those lines, we're going to be putting our numerals. So in this case, I would look at this and say H3PO4 is the most complex. So I'm going to put a 1 in front of it. You don't have to. You could say that, well, maybe on the other side, the PCl5 is where I'll put the 1. You could do that. However, it's possible, not in this case, but it's possible you might take a little bit longer to finish that. In any event, we put a 1 by H3PO4, and we've made a number of statements in this case. So usually it's best in these to balance hydrogen and oxygen last. That's a general rule. If we balance hydrogen and oxygen last, then let's see what we have left over. Well, with this 1 in front of H3PO4, we have 1 phosphorus atom. Thus, there must be 1 phosphorus atom way over on this other side. There has to be. So, in this case, here's the phosphorus containing component, and there is 1 of them there. So I'm going to balance phosphorus on the other side by placing a 1 there. Now, phosphorus has been balanced, but by placing a 1 here, we have made a statement about chlorine. That means by placing 1 there are 5 chlorines on the reactant side. This being, go over to the product side, we see the chlorine containing component. How are we going to balance that? Well, to get 5 chlorines on that side, there's 1 of them on each one. We have to put a 5 in front of HCl. Put a 5 in front of that. So we balanced phosphorus and chlorine now, and we're going to move towards balancing hydrogen and oxygen last. And it's shockingly, that's the last one that we see here that does not have a numeral in front of it. Well, if there's 5, let's count the number of hydrogens on total on this side. Well, there's 5 over here, and there's 3 over there, total of 8. Well, that means there needs to be 8 over on this side. That's the hydrogen containing component. So that in order to do that, to make 8, well, that's H2 comes 2 hydrogens to a packet. I need to put the number 4 there. And if I put the number 4 there, that is 8 hydrogens. Now, there's really no more places to fill in, and we haven't really attacked oxygen. But we would find if we looked at this, 4 times 1, that's 4 oxygens. 1 times 4, that's also 4 oxygens. It does indeed work out. That's not a coincidence. These work out because they must work out. So in this case, it wasn't just lucky that we managed to balance oxygen while we were balancing hydrogen. It works out because it must. All of the ones you will come in contact with on these balancing chemical equations will work out because they must work out. So let's take a look at another example, and this is to highlight something that can be a bit of a shortcut sometimes in these. Now, sometimes we'll look at a chemical equation of reaction and see that on both sides there are multiple atoms balanced as a packet, like a polyatomic ion or something. In this case, we have SO4 on both sides of the reaction. Remember, SO4 was sulfate, that polyatomic ion. So if we want, we can balance that as a packet all at once, instead of balancing sulfur and then balancing oxygen separately. Now, you can do that. It just takes a bit longer to do that. So I'm going to show you how to carry out this shortcut, if you will, by recognizing we have a polyatomic or a packet of atoms that is the same on both sides. We can balance them as a packet. So let's start out here. We need to place a 1 on the most complex. I'm going to argue that that is Al2SO43, and place a 1 there because it's the largest, the most complex, or however you want to look at it. And a good second step here would be to say, if I put a 1 on Al2SO43, there's 1 times 2 aluminum atoms. Let's look at the aluminum containing component on that side. It's just aluminum metal. So if I put a number 2 there, I've balanced aluminum on the other side. So I've balanced aluminum. Now we can go back over to the largest component here and recognize that, oh, I have a SO4 here, sulfate, and it is times 3. Times 3 of, there's 3 sulfates. Remember, there's still a 1 right there. So a total of 3 SO4s. So what does that mean? Well, there better be 3 SO4s on the other side, on the reactant side of the equation. This would be the SO4 containing component. And if we look at that, that is in a packet of 1 by itself. I need 3 of them. So in order to balance SO4 on the other side, I put the number 3 there. Lastly, we have hydrogen over on the far right here. What are we going to do with that? Well, if we look, here's the hydrogen containing component here. We have 3 times 2 hydrogens, total of 6. So what number do I need to put in here to make 6 hydrogens, remembering that H2 is a diatomic, comes 2 to a packet? Well, to balance hydrogen, we're going to put a number 3 in there. 3 times 2 is indeed 6 hydrogens. Now notice again in this case, oxygen is already balanced. If we can even look at that. So 3 times 4 oxygens is 12. Again, 3 times 4 oxygens is 12, times 1 is still 12. Now, again, this doesn't happen by virtue of chance. It balances because it must balance. It has to balance out, and thus we don't need to do a check on oxygen in this case. I mean, it helps to, but we don't need to because these things must balance out. So if you remember in the beginning of this unit of study, we looked at 4 different types of reactions based upon the nature, how the chemical equation of reaction was put forth. We looked at synthesis reaction, decomposition reaction, and single and double displacement reactions. I'm going to go into now sort of what would be considered a weak 5th type of reaction because it defies being labeled as one of those first 4, and we're going to see a lot of these. And it is the combustion reaction of a hydrocarbon. Combustion because it implies burning, and a hydrocarbon because it is made of at least 2 types of elements, hydrogen and carbon. So that's where we get hydrocarbon from there. An example of a combustion reaction of a hydrocarbon would be in our car engine. Here we have octane, which is the component of gasoline. That is made up of carbon and oxygen. In this case, the black pieces are carbon atoms and the white pieces are hydrogen atoms. Now, we're going to find that in this case, in a combustion reaction of a hydrocarbon, always we have oxygen, O2, diatomic oxygen, as a reactant to the point where we don't even need to say it. Well, it just is. And always it is going to have at least carbon dioxide and water as the product, part of the product profile. A lot of the times, the entirety of the product profile of the combustion reaction of a hydrocarbon. We've already looked at an example of one of these, and that was, if you right at the very beginning of this lecture, CH4 plus 2O2 goes to CO2 plus 2H2O. This is a very diagnostic combustion reaction of a hydrocarbon. That is the hydrocarbon, made up of carbon and hydrogen. And look at this, 2O2. So oxygen is always a reactant. Carbon dioxide and water are always products. So this would be easily designated as the combustion reaction of a hydrocarbon. Our task is to balance those, and then we have a specific way of balancing them, very specific, different from the ones perhaps that we've looked at before, but that can be good because we're always carrying these out one particular way. Before we were looking at well, what's the most complex one to put a number 1 by? In this case, we're always going to be putting the number 1 on the hydrocarbon. That may need to be changed eventually, but we will always be putting it on the hydrocarbon. So let's look at some examples. So here's a good example of a combustion reaction of a hydrocarbon. We have C4H10 plus O2, so that goes to CO2 plus H2O. So that looks like a diagnostic setup for the combustion reaction of a hydrocarbon. Wonderful. So there is a set way of carrying this out to begin. And as I said before, the first thing we're going to do is to initially start by placing a 1 on the hydrocarbon being burned. There it is. How do I know that's a hydrocarbon? Because it is made up of hydrogen and carbon, and in this case, so hydrocarbon. So if we put a 1 on the C4H10, we're making a number of statements, specifically about carbon and hydrogen. Typically, the way these are carried out is because the hydrocarbon itself is made up of carbon and hydrogen, we are going to balance carbon first, always, and then hydrogen. So let's do that. What would we do? So by putting a 1 here, that means we have 4 carbons. So we need to balance 4 carbons on the other side. Here is the carbon-containing component of the product profile, and that has just 1 carbon on it. So in order to balance this out, we have to balance carbon on the other side using CO2 by placing a 4 there. Going back to the original hydrocarbon, we're going to see that putting a 1 here means that there is 10 hydrogen atoms here. So we have to have 10 hydrogen atoms in the product profile. Here is the hydrogen containing component, and look at that. In water, hydrogen comes 2 to a packet. So what number do I need to place there to balance hydrogen on the other side? If there's 2 to a packet, to get 10 hydrogens, I have to put the number 5. And indeed, that now balances hydrogens. The way the combustion reaction of a hydrocarbon, solving these are carried out, is we always balance oxygen last. And in this case, both of the product components have oxygen. So we have to do a tally. 4 times 2 oxygens is 8. 5 times 1 oxygen is 5. So that's a total of 13 oxygen atoms. Here's the oxygen containing component, and notice it's a diatomic, O2. 13 oxygen atoms is an odd number. There's no way by putting a numeral, any numeral in this box, I can come up with anything but an even number. So what do we do to get 13 oxygen atoms? Well, when balancing an odd number of oxygen atoms, it's okay to use what are called half fractions on any diatomic. Most of the time we'll be using this half fraction business on O2 because it is part and parcel of any combustion reaction of a hydrocarbon. But it could be Cl2, it could be H2, any diatomic we can use what are called half fractions. The corollary to that, of course, is that we cannot use half fractions on anything but a diatomic. So something like H2O or even the hydrocarbon C4H10, we cannot use half fractions. It is only applicable or possible to use half fractions on a diatomic. In any event, I digress. We have to put a number in oxygen here. 13 oxygen atoms is what we need. The way we carry this out is we put that number 13 in there. So we're going to balance oxygen last as a half fraction. There's that 13. I put it a little high because it's all, if I take 13 over 2 times O2, that's 13, because that 2 on O2 cancels out that half, so that's 13 oxygen atoms. 13 halves O2 is 13 oxygen atoms. Frequently, we can do that, and this is complete as written right now. It's complete as written. It is completely fine. What you may see, and what many like to do, is to clear the fraction by multiplying through by 2, and only 2 on here if you desire. You do not have to. Some people, like me, are sort of anal retentive. I don't like to see half fractions in there. So if I multiplied through all of these numbers by 2, it's still going to be balanced. And if I did that, I'd end up with 2 of the hydrocarbon. That fraction would be cleared to be 13O2. 4 would turn to 8, and 5 would turn to 10. That is a possibility. This is also correct as written. So in this case, there's sort of 2 answers for that. We're going to be looking at other examples of combustion reactions of a hydrocarbon where we actually do get this opportunity. Importantly, either one of those answers that we put up there, either in the numerals in the red or the numerals in the blue, are correct. It's up to you to choose which one you like. Let's look at an example of a combustion reaction of a hydrocarbon that's a little bit more complex. And the first thing we want to look at here is the hydrocarbon itself does not always have to be just carbon and hydrogen. It should be majority carbon and hydrogen, but it can bring along with it, in this case, a couple of oxygens. If it wanted, it could bring along a chlorine or a nitrogen, and that would change up the product profile, certainly. But in this case, notice this hydrocarbon has some extra oxygens in it, which we will need to account for. And also, look at the hydrogens in there. Well, we see some hydrogens here, and we also see a hydrogen hiding over there. So we'll have to be very cognizant of that and careful as we're solving this, because we want this to balance completely. So in this case, we're going to carry this out like any combustion reaction of a hydrocarbon. We're going to place a 1 on that hydrocarbon, or a majority hydrocarbon piece. And so that makes a lot of statements here. What we did before, say, okay, let's balance carbon first on the other side. What are we saying by this 1 right here? What statement are we making? Well, that we have 2 carbon atoms. But be careful. There's another carbon atom hiding in plain sight over here. There's actually 3 of them. So it's important that we scan over the entire hydrocarbon and say, okay, it's not 2. It's actually 3 carbons we have to balance on the other side. A very easy mistake to make. So we have to be careful. In this case, both carbon and hydrogen on this hydrocarbon are susceptible to making a mistake because they're a little bit split up. And sometimes that's just the way that the chemical formula is written. It's just something to keep in the back of your head for when you're carrying out these, or balancing these equations. Fair enough. So as we did before, we're going to balance carbon first. And as always, it's carbon dioxide. CO2 is the carbon-containing component. Over on the reactant side, we had 3 carbons. So because there is a 1 carbon on CO2, we're going to place the numeral 3 in there, and we have now balanced carbon. Wonderful. What's next? Well, like we did before, hydrogen. Notice a 1 over on the hydrocarbon side, there's 5 hydrogens here, but oh, be careful, there's a spare 1 over here, total of 6. Total of 6. So here is the hydrogen containing component on the other side with 2 to a packet, water. So how do I get 6? Well, we're going to balance hydrogen using water on the other side by placing the numeral 3 in there in this case. And as always, we balance oxygen last. Look over here, we see that oxygen is always balanced last. It is lacking in a number there. Well, that's because it's the most complex, and we have to gather now the number of oxygens because both in the product profile contain oxygen. So let's do a rendering here. 3 times 2 oxygens is 6. 3 times 1 oxygen is 3, total 9 oxygen atoms. How do we get 9, ostensibly an odd number, from a packet that can only deliver even numbers because it's 2 to a packet? Well, again, we're going to get those 9 oxygens using half fractions. So we're going to balance oxygen last in this case. So look up at oxygen now on this combustion reaction of a hydrocarbon. We need 9 oxygens, so I'm going to put the number 9 there and always put it over 2. 9 halves times 2 is going to be 9. Always. That 2 cancels out that fraction, so that's 9 oxygen atoms. As before, if we don't like to have a hanging half fraction in there, even though it is correct, we could multiply through all of these numbers by 2 and essentially double them. And that would be another proper way of completing this. So there's, again, 2 correct answers here. Either one would be correct. Now, it should be noted that frequently we can see these combustion reactions of a hydrocarbon can be written out as a word problem. And we're going to have to build the reaction based upon what's in the word problem and then balance it. Here's our example. Aniline, C6H5NH2, burns in the air. Oh, maybe there's oxygen in the air, so that's a hint that oxygen is always a reactant. Burns in the air to give carbon dioxide, water, and N2. Oh, that's a different component of the product profile, but we have to have a nitrogen-containing component in the product profile because we have a nitrogen in what is being burned. So in this case, I would have to tell you that, and indeed I have. Write out the equation and balance it. Well, we take whatever our hydrocarbon is, whatever's being burned, that would be this thing, and set it up exactly with oxygen as a reactant and carbon dioxide and water as a product, and we're just going to put in an N2 component in there in order to balance. So this is what it would look like. A lot of this, since we know that oxygen must be a reactant and carbon dioxide and water is always a product, that's amenable to a word problem. You'd have to build this if you saw a word problem like this. In some of the problem sets for balancing chemical reactions on Blackboard that I've put out there, there are many like this where you have to think about it and cobble together the actual reaction and then balance it. So here we go. What are we going to do? Well, same as before. We're going to place a 1 at the hydrocarbon. There we go. And that makes a lot of statements in this case. Now we can balance 2 things here. We can balance carbon, as we always do, but we're also going to quickly balance nitrogen as well. Carbon, if I put a 1 there, that's 6 carbons. So here on carbon dioxide, which is the carbon-containing component, I need 6 atoms of carbon. So I put a 6 there. But also the nitrogen-containing component. If I put a 1 in front of that hydrocarbon, that means I have 1 nitrogen atom. 1 nitrogen atom. So there better be 1 nitrogen atom on the other side. Well, this comes 2 to a packet. How do we get 1 of them? It's a diatomic, so it's okay. This diatomic is N2. That's one of our diatomics. I need 1 of them, so I'm going to put 1 in there divided by 2. A half of N2 is 1 nitrogen atom. So indeed, we've kind of done a twofer here. We've taken out carbon and nitrogen. And now we're going to move over to hydrogen. Let's look on the reactant side by placing a 1 right here. We make a statement now about hydrogen. There are 5 hydrogens here. Be careful now because there's more. 2 hydrogens there. Total of 7 hydrogens. Now, this is maybe a problem. 7 hydrogens. How do we balance that? This is the hydrogen-containing component of the product profile. Hydrogen comes 2 to a packet. I need 7, an odd number. How do I do that? Well, let's remember our half fractions. I could put, to balance hydrogen using H2O, I could put 7 divided by 2. 7 halves. 7 halves H2O. So there are 2 hydrogens times 7 halves is 7 hydrogens. But now we have alarm bells going off. We have alarm bells going off because H2O is not a diatomic. H2O is not a diatomic like N2, like O2. So we have a problem. Before we can move forward, we have to clear that fraction. We must clear it. That 7 halves does not fit with a non-diatomic. So how are we going to do that? We're going to multiply through, even though, now look, we haven't even been able to put a number in for oxygen. We have an emergency. We have to multiply through with the numbers that we have by 2. We have to do that. So occasionally half fractions can be established on non-diatomics, but it's an emergency situation. In these cases, we immediately multiply through by 2 in order to clear the non-diatomic half fraction. So let's do that. Multiply through by 2 to clear the H2O fraction. There it is. I did that all the way through. So notice what we did here. That turned our 1 here to 2. Our 6 that was here to 12. Our 1/2 on the nitrogen to 1. And most importantly, the 7 halves that we had on the non-diatomic into 7. So now that our disaster has been averted, we are going to continue by balancing oxygen last. So let's now take a tally of the oxygen atoms. 12 times 2 is 24 oxygen atoms. 7 times 1 is 7 oxygen atoms. Add them together, 31 oxygen atoms. So that means we need 31 oxygen atoms on the reactant side. How do we get that? Well, 31 is an odd number. So we can do a half fraction on our good old friend diatomic oxygen here. We just have to put 31 in there divided by 2. 31 halves times O2 is 31 oxygen atoms. Now, as before, if we like this, this is the correct answer. If we want to get rid of those half fractions, we can always multiply through by 2 if desired. And in this case, if we did that, that would change up all of these numbers to the numbers in blue that we see here.